Okay, so in this talk I will discuss a topic which is not new, the calculation of the abundance of relic QCD actions. It's a topic like maybe 20, 30 years old, but there has been a revival in the last 2-3 years on this calculation. So let me go through. First, give some very basic introduction. So whenever you have a light particle, in this case, you can think of neutrinos or AXIONs, for instance. Then the basic quantity, which is relevant for the calculation of the present day abundance, is the total number of degrees of freedom of the plasma, G star, okay, the sum over bosons and fermions. In the standard model, G star has a very steep growth around 100 MeV, which is the QCD phase transition, above 100 MeV here. And this is precisely a region of interest of AXION production here. So as I will show, it's important the fact that G star changes rapidly there. Okay, but the very basic ingredient is that, as it is well known, the entropy conservation of the plasma tells us that G star to the 1/3 times T scales like 1 over the scale factor. So whenever there is a change in G star, the temperature of the plasma, of the standard model plasma, essentially stops being diluted, has some small heating, okay, gets heated. However, if you look at the particle which has decoupled before this heating, that particle itself does not get heated. So when you compare a thermalization rate of a particle, let's call it gamma, with Hubble, then that determines the decoupling epoch. After that, they simply freely evolve if they are essentially massless. And then when you compare the energy density of the relic particle compared to the photons, there is a suppression due to exactly to this heating of the photons, which is nothing else than a G star factor at the coupling epoch to the power of 4/10. All right, so for example, in the case of neutrinos, it is well known they decouple at MeV, and after the decoupling, just after that, electrons and positrons become non-relativistic. Therefore, there is a jump in G star, which suppresses a bit the temperature of neutrinos. Indeed, the neutrinos have only about 2 Kelvin instead of the 3.7, instead of the 3 Kelvin of the photons. Okay, it is traditional to parameterize any contribution from a massless particle, from essentially massless particle, as extra neutrino species, but this is just the name. Okay, and the basic quantity is delta NF is nothing else than the ratio of the energy densities of the relic abundance, of the relic energy densities today, or at the CMB time. All right, so for a scalar, which is the case of the QCD axion, this is the precise correspondence. The plot from G star tells you immediately what is delta NF, just 1 over G star to the 4/3, so you get this type of plot. Now, you can immediately read that a particle that decouples at temperature smaller than the QCD phase transition here has a relatively high delta NF, which can be probed already by present experiments like Planck, for instance. Okay? So the present bound is around 0.3. Therefore, a particle cannot decouple later than 0.1 GeV. Well, not much later. And the axions will be precisely the interesting region for axions is precisely decoupling in this region. It could be also much higher, but of course, if it is much higher, delta NF is much smaller. All right. As an extra ingredient, the axions they do have a mass. They are not totally massless. And just like the neutrinos, this mass becomes relevant at late time after CMB epoch, if you want. So they become non-relativistic after CMB epoch, and therefore they, in the present epoch, they contribute to the dark matter actually, not as radiation. And so that gives further constraint because matter, an extra component of dark matter, is more constrained. Okay, very brief introduction.
Can I stop you?
Yes.
Because otherwise I get instead of one of the G star should be the G after divided by G before.
Yeah.
It's not the same. Can be very similar with the two numbers. Like 4/11. It's
Yeah. There is
not terribly small.
no, but at the high temperature is going to be small. If it decouples at high temperature, it's very small.
No, but the entropy production should be G star before the decoupling divided by G star after the decoupling, which it's a small jump.
For neutrinos. For neutrinos, it's a small jump. For actions, it's a larger jump.
Okay.
No, but in the end, what matters is today is the at CMB time compared to the time of production, because it is the ratio of the energy densities after all the evolution of the pole.
Okay.
Yeah. Okay, so the case that we want to study is the QCD action is in its minimal formulation, meaning that we do not assume any in this talk. I will not assume any extra coupling, just a coupling to QCD, which is the one which is needed by definition to define the QCD action, because well, the QCD action is a solution to the strong CP problem in QCD, which is the question: why is the CP violation so small in QCD? And CP violation is parameterized by this parameter theta in front of this operator. We know that this is very small in the standard model, and the solution of the QCD action is to promote this parameter to a field in units of this constant FA, which is called decay constant. And naturally, the action potential gets minimized precisely when the action is 0. Therefore, that explains why theta is so small today. In addition, we get a very light scalar particle. The mass is given roughly by the inverse of this coupling 1/FA times the QCD scale square. So the ballpark is around less than an electron volt for an FA, which is larger than 10 to the 7 GeV. And by astrophysics, we are constrained to be larger at, say, that 10 to the 8 GeV, actually, roughly. So the mass is going to be smaller than 0.1 electron volt, typically. Okay, but we want to not to use astrophysics here. We want to use cosmology. So from cosmology, the action is very interesting because it is a dark matter candidate in the form of the so-called cold actions. But in reality, there are two populations. One is the cold actions, which I will not talk about. And then the other population is the thermal actions, which is the topic of this talk. Okay, so for thermal population, we can study what happens at very high temperature. At very high temperature, the action scatters with gluons because it is coupled with two gluons. And just by dimensional analysis, the rate is going to be temperature cube over the constant square, Fa square. Comparing with Hubble, one immediately realizes that at high temperature, they are in equilibrium. So this is a very similar situation to what happens with the neutrinos. And the decoupling temperature is essentially just by equating these two quantities, and it is typically for Fa larger than 10 to the 8 is around or above lambda QCD. Okay, so that's immediately what comes out. Okay. All right. So this calculation is actually, as I said, is not new. It has a long history, and there are several treatments to. Essentially, what we want to know is the abundance, right? So we want to know the thermalization rate. The most naive treatment is the instantaneous decoupling. If you know the rate, just equate to H, and then that gives you immediately the abundance. The next level approximation is to write the Boltzmann equation. And the typical approximation is to write one single Boltzmann equation for the total abundance. We go beyond this approximation because we actually improved this treatment by using, first of all, momentum-dependent Boltzmann equation, which turns out to be rather important. And also, we recomputed the scattering rate here, taking into account the fact that perturbation theory fails actually in this regime. Okay. So the momentum-dependent Boltzmann equation is nothing else than a differential equation for the occupation number that gives creation and destruction of axions. There is also a Bose enhancement factor. And we need to compute what is this gamma creation or annihilation. And the standard treatment is to integrate overall momenta of the other particles. And what we focus on is the production below the QCD phase transition, meaning where the plasma is dominated by pions. Okay, so essentially the calculation is about the thermalization rate of pion-pion into axion-pion. At leading order in chiral perturbation theory, which is the theory of QCD at low temperature, if you want, the theory of pions, one can compute this amplitude and finds this result. Okay. However, it was recently pointed out by this paper by Di Luzio, Martinelli, and Piazza that this amplitude actually breaks down above 60 MeV, which is in the regime of interest of our calculation. Okay. So our aim was to cure this problem, and but just by looking at all the literature, actually, one realizes that the same problem exists in pion-pion scattering, where above roughly essentially the same temperature, 50 or 60 already in this paper 94, the leading order prediction, which is this line, deviates strongly from the one loop correction. So it is exactly the same problem. And they cured it by using a phenomenological approach, essentially by using experimental data, if you want, here. Okay. Because here we are completely beyond the perturbation theory. Okay, so what we did was simply to realize that the axion in a certain basis can be written as a pion, essentially. It mixes with the pion by a mixing angle, theta a pi. And the leading contribution at in momentum, in an expansion for high momenta, the leading contribution is going to be the same from the pion-pion scattering and axion-pion scattering. Okay? So essentially, the matrix element of axion-pion can be reconstructed from the pion-pion, apart from errors which are subleading in m pi square over s. So this can be checked explicitly at 3 level. At 3 level, the two expressions are the same, apart from these subleading contributions. And it can be checked explicitly also at 1 loop. The full calculation is available in the literature. So we extended the full phenomenological treatment also to the axions. So essentially, we took the experimental data from the pions and we multiply by the mixing angle. And so what we get is this rate, which compared to the leading order actually goes down after 100 ml. So that's the first ingredient. It's also in agreement with this paper that came out later. This gives us a lower bound on gamma. Why I said this is a lower bound? Because there could be other channels involving other particles like kaons, nucleons. They are supposed to be subdominant, but it's very hard to compute them because you get closer and closer to QCD phase transition when they become relevant. Okay. Then let me discuss the momentum dependence, which I advertised at the beginning. It was important. Why is it important? Because if you write down the rate as a function of the momentum of the axion, it has a non-trivial dependence. Okay, this is a different plot. It's not the same plot as before. This is with momentum in the horizontal axis. So you realize that axions of higher momenta have a stronger coupling to the plasma. Therefore, they decouple later than axions with lower momentum. And this means that the ones that decouple later, they actually see a different photon temperature. They see a different G star, okay, when they decouple. Therefore, they are more abundant, the ones that decouple later. That means that you get more axions at high momentum than at low momentum compared to the standard Bose-Einstein distribution. And indeed, by solving the differential equations in momentum space, you find a distribution which has more power in the UV than the Bose-Einstein distribution. And this leads to an enhancement of the total abundance of about 40%. Okay, why, by the way, why for the neutrino this is not so relevant? It's not a 40%, because for the neutrinos, the change in G star is not exactly happening at the same time of decoupling. They are slightly separated. And this separation suppresses this effect and gives only 1%, which is the origin of this famous 3.040 something. It's mostly due to this effect. Okay. Finally, let me show the results. So this red line shows the present bound. Okay. In the horizontal axis, you have the axion mass. And here you have, if you want, the parameterization of the abundance, which is delta N effective. So what we find after running a cosmological analysis with CFD data is that the axion mass cannot be less than 0.24 electron volts from cosmology. By the way, let me stress also that it's non-negligible the fact that there is a finite mass. It's not just pure radiation, because by ignoring the mass, the bound would be here. Indeed, with the mass, goes down by quite a lot. And then, yeah, this is our result, 0.24 electron volts. And then, interestingly, let me also talk about a little bit about the future reach. So future reach means that future experiments, Simon's Observatory, CMB stage 4, will be able to probe also a region with smaller delta N effective, which is around 0.1. And this is precisely around the QCD phase transition, or above. Now, calculations here are very hard because around the QCD phase transition, everything is completely non-perturbative. So one has to go to lattice QCD calculations. And this has not been done yet. Well above the QCD phase transition, there are perturbative results using gluons, as I mentioned at the beginning. But they are also plagued by uncertainties because these results are actually divergent because there is an infrared divergence. Therefore, one has to cure these results by suitable treatment. And it also is a source of large uncertainty. Okay? Indeed, let me just discuss in 1 minute this high temperature perturbative result. So it can be parameterized as T cube over F square times an unknown function that people call F3. But this function is divergent, okay? You have to regulate it by putting a mass for the gluon, a thermal mass for the gluon. But that is not sufficient because you can see from this log, when G strong becomes large, the log becomes negative. Therefore, the rate becomes negative, which is totally unphysical. This has been cured by this paper in 2013, Salvio Strunaxue. However, this cure is formally valid only for small G strong, while we are talking of large G strong, which is the region at low temperature. And in that region, extrapolations have been claimed to be applicable, but there is a lot of uncertainty because you are beyond the regime of validity. Moreover, it has been used, this rate, to glue, essentially to extrapolate, to gluing to the pion rate. But this is not correct because the pion rate is suppressed by an extra factor, which is exactly the mixing angle. And you can see that this mixing angle goes to 0 when mu is equal to md. While the gluon rate has nothing to do with this suppression. Okay, so you are matching two quantities which you should not match because one goes to 0 in one limit, the other one does not. Moreover, the pion rate is not monotonic with temperature; it goes up and down, so it's very difficult to match two quantities that go up and down. All right, so let me also mention last slide that we estimated the effect of the so-called sphalerons, which have been studied for zero momentum axions, so for homogeneous configurations. They are semi-classical effects where dissipation effects. So you can infer a dissipation rate from the Sphalernon rate. This is subdominant at high temperature, but if you extrapolate it, which is just an exercise, I'm not claiming this is the right result, it's simply an exercise. You extrapolate it to low temperature, then the Sphalerons becomes larger than the perturbative calculation, showing that it could be that there are non-perturbative effects which are larger than the perturbative rate already down below 5 or 10 GeV, which is, and then you enter in the fully non-perturbative region, which is around 1 GeV. Okay, so by sorry, this is really the last slide. One can estimate this non-perturbative region by simple, very, very naive dimensional analysis. So it's t cube over s squared times a coefficient. This coefficient reasonably could be of this order, 0.1 or 0.01. It has been actually very recently confirmed by a QCD simulation that the Falleron coefficient is in this ballpark, which means that for masses of less than 0.1 electron volt, one can still get delta N effective, which is measurable by future experiments. Of course, this requires better calculations, but we could be in this ballpark. Okay, conclusions. We have computed more reliable pion action rates, more reliable than the 3-level calculation. Okay. And we got this new upper bound from cosmology. Then we also found for the first time the importance of momentum-independent Boltzmann equations for actions. It is very important because G star changes very abruptly. Finally, 2 comments. The perturbative rates that have been considered for a long time are doubtful, let's say, when you go down close to 10 or 1 GeV, let's say. And then, crucially, non-perturbative rates are important, but they are not available yet from lattice calculations. To exploit precisely the power of new experiments from CMB that will probe that region.